Now, in the previous theorem, what we have concluded that if the identical equation has the two roots and the difference of that two roots is non-zero and not an positive integer, then you are able to write down two linearly independent solution of the differential equation of this type, which has regular singular point. The question is, if we have m1 is equal to m2, or this m1 minus m2 is an integer, then only we have one solution of the differential equation. So in that situation, what we can do? That means what will be the another linearly independent solution? So solution to that, we have another theorem which tells you that if one of the solution of the ODE y double dash plus p of x y dash plus q of x y equal to 0 is y1, then second, I may write down this is in short linearly independent solution of this equation, let's say 1, is given by y2 equal to v into y1, where what is this value of v? Where v equal to, or instead of v it is actually v dash. So this value of v can be calculated by integrating this v dash, because this is v dash is the differentiation of v, which tells you that 1 upon y1 square into e power minus p dx, which is a non-constant function. Okay, so this is very important result actually, which gives you the another solution, or when you will have one linear independent solution, what will be the another linear independent solution can be calculated using this. Y2 is equal to v y1, and where the value of v you can calculate using this expression. So now it is picture is clear to you. If you have a differential equation which has the x is equal to 0 as a regular singular point, then first step is to calculate the identical equation. If this identical equation has a two roots and the difference of these two roots is non-zero or not a positive integer, then you are able to write down two linearly independent solution in regular manner. If this differential or this identical equation has m1 and m2 and their difference is 0, then or 0 or it is an integer, then you can always have the one solution. To get the another solution, you have to do this thing. Okay, so let us try to prove this is as a theorem. So let us discuss the proof of this. So given that y1 is the solution of equation 1, since it is a solution, it must satisfy this given equation. That means it is y1 double dash plus p of x y1 dash plus y1 equal to 0. This is the solution is there. Let us assume that y2 equal to vy1, which is given to you. This is the thing. And the first time the whoever is thought of this one, it may be a genius, because how this come into the picture, we don't know. But we assume that the y2 will be this. Is also a solution of equation 1. That means it must satisfy this equation, and we also assume that v is a non-constant function. Otherwise, if it is constant, then it is linearly dependent. It does not have any meaning. That's why I'm assuming it is as a non-constant function. So it must satisfy this also the same equation. So that's why we have y2 double dash plus p of x, y2 dash plus y2 equal to 0. I may call this as equation 2 and this is as equation 3. Okay. Now let us calculate what is y2 dash, y2 double dash, and then we substitute that value here, because y2 we have here. So y2 we have this v into y1. So y2 dash we will have it is, because v is also function of x, y1 is also function of x, we can have it is v dash y1 plus v y1 dash, and y2 double dash we can have it is v double dash y1 plus v dash y1 dash plus v dash y1 dash plus v y1 double dash. You got this, I think so. That is the product rule for derivative I have used here. Now substituting this value of y2, y dash and y double dash into the equation 3. So using 3, we substitute this value, so it is v double dash y1 plus v dash y1 dash plus v dash y1 dash v y1 double dash plus p of x into y dash is this, so it is v dash y1 plus v y1 dash plus q of x into y, that is v y1 equal to 0. Now let us rewrite or rearrange this equation and let us write down into another form. So we can say that this is v double dash y1 plus v dash. So that is a term of v dash which is here y1 double dash y1 dash, and which comes 2 times here and here. So that's why it is 2 y1 dash. There is another coefficient of v dash is y1 into p of x. So it is plus p of x into y. There is no term of now v dash is there. Plus v. So that is a term of v is there. That is this term we'll have here. So it is y1 double dash. When you multiply this with this one, you will have v. So it is plus p of x into y1 dash plus the last term is there, this one, that is q of x into y1 equal to 0. Now what is this quantity? Using equation 2. Using equation 2, we can say that this quantity is 0. So that's why we can have v double dash y1 plus v dash 2 y1 dash plus p of x y1 equal to 0, because this quantity is 0 due to the equation 1. So only we have this two term. So that I have written here. Fine. This we can rewrite as y v double dash upon v dash equal to 2y1 dash plus p of x y1 upon y1. Integrating both sides. See, what is this? It is a derivative, is up. That's why it is log of v dash. Here, this I can rewrite as 2y1 dash upon y1 plus p of x. This we can write down. Okay, because y1 upon y1 is there. So that's why this we can write this. Here also the derivative of y1 is up. So it is minus 2 times log y1. And also this plus sign goes on the other side, so that's why it is minus. It is also minus, so it is also again minus. Integration p of x dx is there. Now this I can write as log of y1 raised to minus 2 plus log of e power minus of integration p of x dx we can write. So that's why if I now apply antilog both sides, this will gives you v dash is equal to y1 raised to minus 2 into e power p of x dx, integration of p of x dx. So this is the value of v dash we have. Is the theorem is over? We have proved this. The value of v dash will be this. Is the theorem is over? Is there anything to prove yet? Let's see what is the statement. The statement is this. You just observe what should be left to prove, or a theorem is over. The thing is, we have to prove that y2 is this, is the another solution. We have proved that if y2 is this one, then v1 will be this, and it must satisfy this equation. So that means this is the solution and this is the quantity we have. What is the left quantity is Li. We yet not prove that if y2 in this form, then y1 and y2 are Li. So as I told you, how to prove that two functions are linearly independent, then you have to start with this linear combination c1y1 plus c2y2 equal to 0, and we have to show that any one of them is non-zero. Okay, so what we are trying to prove is these are linearly independent, y1 and y2. So if we have started with a linear combination, and if we got this c1 and c2 both of them are 0, then they are not linearly independent, then they are dependent. Okay. So here I want to prove that any one of them is non-zero. So without loss of generality, I may assume that c1 is non-zero. If c1 is non-zero, let's say c2 is non-zero. If c2 is non-zero, we can write down c2 upon c1, sorry, c1 upon c2, y1 plus y2 equal to 0 by dividing c2 both sides. Let us take this c1 upon c2 is c. So assume this. That's why it is c into y1 plus y2 equal to 0. So therefore y2 will be minus of c y1. What is the value of y2? We have it is Vy1 equal to minus Cy1. Then y1 is cancel out because it is a non-zero, it is a solution, and v equal to minus c. Since v with c is constant and we have v which is non-zero constant, sorry, non-constant, we have a non-constant function. Since this v is non-constant function, this is the contradiction. So here we have a contradiction. Due to this contradiction, C2 will never be 0. So that means C1 and C2, both of them are 0. Since both of them are 0, we can say that y1 and y2 are linearly independent. If any one of them is non-zero, then they are dependent, as I told you. So this proves this statement of this theorem. Okay. So I think so I should stop here for today. There is one more theorem is there, but we will not discuss that proof of that theorem. I'm just discussing the what is the statement. And we will do this is using the example itself. So the thing says discuss the method of solving this equation y double dash plus p of x y dash plus p of x y equal to 0 when identical roots of identical equation differ by non-zero negative integer. That means what will happen if it is a integer? What will be the method and how to calculate? This is the way, this is the things we can have. So for that, suppose that x is equal to 0 is a regular singular point of ODE 1. If I call this as equation 1. And let m1 and m2 be two roots of identical equation suppose that the one solution, that is y1 x power m1 summation n running from 0 to infinity a n x raised to n, this is always it will have, okay, is Frobenius series solution of equation 1 if this m1 minus m2 is 0 or a positive integer. Then the general form, this is very important, no? General form of another linearly independent solution is this y2 equal to log of x y1 plus x m power m2 summation n running from 0 to infinity a n x raised to m. We will not discuss the proof of this, but the another solution you can write down in this form. That is very important. The another solution of the differential equation we can write down into this form. Okay. So it says that if this difference, so in the previous theorem we have discussed the how to calculate, and the formation or general form it is given into this form. Exactly this y2 can be calculated using this way. So it is log of x into y1 plus whatever the another solution is there. So